So today we are very lucky to have Alfred McEwen here, who is a true geologist, I would say, has a BS, an MS, and a PhD in geology from Northern Arizona and Arizona State. He's published dozens of papers, a few books, has a long history of planetary mission involvement, including Galileo, Cassini, of course, he's PI HiRISE, MRO, PI of Ivo, that hopefully maybe one day may fly. I have my fingers crossed. And then, of course, today he'll be telling us about his work as deputy PI on one of the instruments, and of course, the mission as a whole for Europa Clipper. So, take it away.
Okay, so I'm going to try to give an overview of the mission, and just to make sure everyone's on the same page. I'll introduce you to the Galilean satellites. There's 4 of them. The Earth's moon is about intermediate in size between Io and Europa on the left here. You can see them on the right in an HST image. Look tiny compared to Jupiter, but they're large moons. There's a density gradient from Io, which is 3.5 grams per cc, iron and silicate. Europa, mostly silicate, and Ganymede and Callisto have a lot more ice in them. It's also cratering density. No impact craters at all found on Io. Callisto, back-to-back craters. Europa, very few craters. This is the exact opposite of the pre-Voyager. Voyager 1 and 2 spacecraft in 1979 gave us first good look at these moons. But because of the focusing effect of Jupiter's gravity, Io should be bombarded more and at higher velocity, making bigger craters with the opposite gradient. What happens is there's tidal heating that they didn't know about back then, which resurfaces in the opposite direction. So what we think we know about Europa's interior is shown here. It doesn't have an intrinsic magnetic field. There's an induced magnetic field that's quite important to studying the ocean. So the core is thought to not be convecting. The radius uncertainties, diameter is uncertainty because of unknown sulfur content. And then the gravity data from Galileo says that there's an ice layer. Oops, can't point to this. It says that there's an ice layer about 150 kilometers thick, or there's the H2O layer. It's a combination of ice and water. And there's debates about just how thick is the ice shell. In contrast, Earth's average ocean depth is only 4 kilometers. There's an induced magnetic signature that's consistent with a conducting layer in the subsurface. And so globally interconnected salty water is the favorite explanation. But there are no other geophysical measurements yet to confirm that there's an ocean in Europa. There are surface features interpreted as evidence for an ocean. And the bottom bullet that you can't read says that the thickness of the ice shell is debated. Most workers say from 10 to 50 kilometers. So Europa has about twice as much free water, ignore that water in the mantle, but free water is water or ice than does Earth. And Mars is there just to say, Mars is it's all dry, ignore Mars, that's why it's there.
Oops. Oh, we gotta do that. Let me come.
Well, okay, I'm just going to go on anyhow then. So Europa may have very sparse life, but unless there are hydrothermal vents on the ocean floor, as there are on Earth, and this is an NOAA spectacular video of a black smoker with all of the different life forms that exist in black smoker. So that's the video you're missing if you're online.
Oh, no,
sorry.
Yeah.
So this also shows some videos.
Does it work now?
Works.
So the audio
Thank you.
doesn't work? Okay.
So what makes Europa interesting, while there might be hydrothermal vents on the ocean floor, is tidal heating. And that tidal heating is because of an eccentric orbit around massive Jupiter, and the eccentric orbit is because of the Laplace resonance. Every time Ganymede orbits once, Europa orbits twice, and Io 4 times, so they periodically line up. This forces the orbits to remain eccentric. Tidal damping doesn't circularize the orbits, they remain eccentric. And this, at least for Io and Europa, and so they are tidally heated. Io maybe 10 or 20 times as much as Europa. This tidal heating likely changed over time as the orbits and thermal states evolve. Could be complicated history. Where the heat is generated is a major open question. Tidal heat could be generated in the core, mantle, ocean, or ice shell, or more than one of those. Okay, Europa's surface, there are very few large impact structures, and the estimated average age of the surface is around 15 million years. So that's extremely young, geologically speaking. Clearly, there's been a lot of geologic activity since the early ages.
We have an online question,
Yeah.
which is why is tidal heating dependent on the eccentricity of the orbit?
Right. So this first one, we go back and make that first movie running again. You can see as it goes around its eccentric orbit, it gets closer, further away from Jupiter. This changes the entire shape of the planet. So it stretches out back and forth, and this heats the interior of the planet, basically, just like bending a piece of metal back and forth. So what does cover Europa's surface? There are these ridges or lineaments all over Europa. It's like a ball of strings where lineament on top of older lineaments, on top of still older lineaments all over the place. Many of these are double ridges, as you can see here. And we have lots of hypotheses for how these double ridges form. I won't go through all of these, but these are all testable with Europa Clipper data. There's also chaos terrain where this ridge plane appears to have broken up and rafted apart, and some of the ridge planes are destroyed, some of it's tilted on edge, looks kind of like collapsing Antarctic ice shelf.
Just out of curiosity, pardon my curiosity, but sort of how old or young is that area where it still bears a signature of something that happened that has been erased by?
Yeah, so we wish we had radiometric dates for the surface areas. All we have are craters. There's very few of them. It's tough to say from what we have now. It does seem though as if the chaotic terrain is generally younger than the ridge planes, but that's still debated, and there could be cycles. There are some new ridges that form on top of the chaos. You can see some of those here. So both are active, or geologically speaking, and we'd like to know a lot more about what's active today and what's active recently on Europa. That's a good goal for Europa. Okay. There's also these bands that apparently have the crust that's spread apart. And here you can see you can reconstruct it, and all the lineaments match up, so you know it used to be that way. You can also see that this started off as a double ridge, or a couple of different double ridges that decided to start spreading for some reason, and the others don't spread. And here's a little cartoon of convection in the ice shell that might explain the spreading of these spreading bands. This might also explain chaos terrain. There are it's almost funny that multiple hypotheses keep getting reused for different features on Europa. We don't know which ones are really correct. Hey, Europa Clipper. There was a whole book written about this mission by David Brown called The Mission. And the cover of the book says, how a disciple of Carl Sagan, an ex-motocross racer, a Texas Tea Party congressman, the world's worst typewriter saleswoman, a California mountain people, and an anonymous NASA functionary went to war with Mars, survived an insurgency at Saturn, traded blows with Washington, and stole a ride on an Alabama moon rocket, fortunately not, to send a space rocket to Jupiter in search of the second Garden of Eden at the bottom of the alien ocean inside of an ice world called Europa. A true story.
Yeah.
So Europa, getting a Europa mission has a long history. starting with the Europa Orbiter back in 1996 to 2002. This was in the faster, cheaper, better era of Dan Golden, but it's not easy getting an orbiter around Europa. The cost kept going up. It was canceled. Then we got a new NASA administrator, Sean O'Keefe, who came from the nuclear-powered submarine world. He said, we need nuclear fission-powered spacecraft to really power the solar system. They came up with this GMO, Jupiter Icy Moons Orbiter, that was supposed to first orbit Callisto, then Ganymede, then Europa. This thing turned into a huge Battlestar Galactica. We didn't have a launch vehicle to be able to launch the thing at the time. Cost estimate kept going up. Okay, that went away. Next was Jupiter Europa Orbiter. This was joint with European Space Agency, the Laplace mission, the whole thing was called. But then we had the decadal survey in 2012 that did an independent cost estimate of $4.7 billion. And the Europa people went, oh my God, that's outrageous. It couldn't possibly cost that much, but nevertheless, it got canceled or didn't go forward rather. ESA did approve their part of this called the JUICE mission, Jupiter Icy Moons Explorer, that launched in April of this year. So then the next iteration was Europa Clipper. So this is intended to be much less expensive than JEO. And there was this Tea Party Republican called John Culberson, who loved Europa for some reason, and he kept injecting money into the NASA budget. He was chairman of the House Finance Committee. And NASA didn't want a new start for Europa, but he kept giving them money anyhow, year after year. Then plumes were detected from Europa, maybe. Still controversial, but that helped a lot to convince NASA, I think, to give it a new start in 2015. Current cost is about $5 billion. Awfully similar to that $4.7 billion estimate from previously. There's a couple of good excuses here, mixed in with some maybe not so good ones, but Europa Clipper was required by the Senate to launch on the Space Launch System, which didn't exist yet. But of course, there was a lot of skepticism about whether it would be available. So you had to design it for both this non-existent launch vehicle and when it did exist. And the Space Launch System, nothing was known about the launch environment, the loads. So you had to over-design the spacecraft. A lot of money was spent for that. Then COVID hit at just exactly the worst possible time during peak activity of Europa Clipper, peak payload of marching army, building instruments and spacecraft subsystems. So those are two excuses anyhow. Now there was also a Europa lander. This is what Culberson really wanted to do, was get to the surface and discover life. But he was convinced that you needed Europa Clipper first before as a precursor for the lander to know something about Europa, where to land, and how to design the lander. He kept inserting funding for Europa Lander as well, but then he lost re-election. His opponent accused him of caring more about water on Europa than water in Texas. And then Europa Lander was not recommended in the most recent decadal survey, so that's not in the works anymore. But Europa Clipper is in good shape. So what changed is that Clipper does not orbit Jupiter. It does not orbit Europa. It orbits Jupiter and makes many close flybys of Europa. And this manages the radiation dose a lot better. And it can be a longer mission with more data return. But of course, there are disadvantages as well. Okay, so Europa Clipper started off with 5 major objectives. The overall goal is to explore Europa to investigate its habitability. So that includes understanding the ice shell and ocean, composition of the surface, the ocean, the exosphere, geology, geologic processes, current activity, and reconnaissance for a future lander was one of the prime objectives. That's since been demoted to a subset of geology. This is the origins workshop. You may ask, where's origin and evolution here? Well, let's go back to the Laplace mission here, which included Jupiter Europa Orbiter. And the science goals of the Laplace mission included what had been the conditions for the formation of the Jupiter system, how did they relate to the formation scenario of the solar system and other planetary systems, They contribute to the possible emergence of life. How does the Jupiter system work? How well do we understand it as a system level? How does the system contribute to conditions for habitability? And third is Europa habitable. Europa Clipper was descoped to just that third bullet, is Europa habitable? That's why origin and evolution are not part of the science objectives, but the Europa Clipper measurements are going to be excellent for origin and evolution, at least of Europa. There's a mass spectrum, both a gas and a dust mass spectrometer that can measure isotopes. And the JUICE mission is there studying the whole system. So we're going to essentially get the Laplace mission here in the end. So habitability of Europa, what is it? And how will Europa Clipper address it? So habitability means the environment contains the chemical ingredients and physical conditions clement for life, and life considered extreme on Earth. You need a solvent. Water, as far as we know, is the only one that works, but not necessarily. And habitable does not necessarily mean inhabited. Sometimes this is simplified to water composition and energy. At the right is a nice diagram showing you a number of nice diagrams that have been produced for a series of papers in space science reviews that are just coming into press now. This diagram shows various environments in Europa's subsurface that might be habitable and various processes that are relevant to habitability, including producing oxidants and reductants for chemical energy. This is just a plot of life on Earth, temperature versus pH. And just to say that extreme life on Earth exists over a much greater range of conditions than does familiar life, which is the green box in the middle there. Okay, Europa Clipper has 10 science investigations. 5 of them are remote sensing and 5 of them are in situ. The in situ includes, as I mentioned, a gas mass spectrometer, MASPEX, a dust mass spectrometer, SUDA, magnetometer, plasma instrument, and gravity radio science for the deep interior of Europa. Remote sensing includes Europa-UVS, ICE, Europa Imaging System with 2 cameras, an infrared spectrometer, thermal imager, and an ice penetrating radar. I'll say more about each one of these briefly. I can't cover all of these in detail. Europa-UVS studies primarily the atmosphere and plumes, if they really exist, including composition, detection of plumes, even if the plume is invisible, small at visible wavelength, lack of fine particles. If it's just gas, they can still detect it. Europa Imaging System, ICE. The PI of this is Simi Turtle, an alumna of this institution, and I'm deputy PI of ICE. There's 2 cameras, a narrow angle camera, which is on 2-axis gimbals. So we have a lot of pointing flexibility with the narrow angle camera on the NAC. There's also a wide angle camera that does systematic color and stereo mapping. I won't read a lot of the information on these slides, but there's time for questions at the end here. Advertise ICE a little bit more here. Left here is a map of the coverage that's accessible to the NAC. We can't cover these big areas at better than 10 meters per pixel because of just time, the timeline and data volume. But we can get nearly global coverage at better than 50 meters per pixel. This was one of the things that they thought they were giving up in going from Jupiter Europa Orbiter to Europa Clipper. Can't get global, easy to get global coverage with an orbiter. But by adding these gimbals, which was a gamble because it's the instrument much more complicated, we're able to get this back and also do other things with the gimbals. On the right there is an illustration of the wide angle camera, a long track stereo coverage as we fly over the surface.
Can you say what your best resolution is going to be? I'm assuming you have a special mouse approach on occasion.
I'll show you.
Okay. Oh,
There you go.
That's nice.
That's a 0.5 meter per pixel image of part of Antarctica. We'll get that scale. Maybe a little better at 25 kilometers if it's well illuminated and bright enough for seeing noise, but at least this we get over very small areas of space. Okay, MISE is a mapping spectrometer. It goes from about 0.8 to 5 microns. This will produce maps of the key compounds on the upper surface. Now, the ice bands are very obvious and easy to map. Shape of the ice band is varying somewhat by the composition of salts. What's really challenging about this experiment is to try to detect organic material. We don't know that it exists on the surface, but we want to find out and definitely map it out if it does. But the absorption bands for organics exist in the 3 to 5 micron region, where the water ice makes the surface to first order black at those wavelengths. So you need very high signal to noise ratio. Europa Thermal Imaging System, E-THEMIS, has 3 band passes in the thermal IR. This is primarily to look for any sort of endogenic thermal anomalies. We did see these. We see this all over the place on Io. We've seen this also on Enceladus in the south polar region. So you might, for example, see warm area in the middle of these double ridges, or we might not see anything with it. We don't know that they're there. It could also tell something about surface properties. Now, reason. This is radar for Europa Assessment and Sounding ocean to near surface. There's another ice penetrating radar called RIME on JUICE. So they really wanted to have rhyme and reason. So they invented this acronym, come up with reason. But this is quite the experiment, by far the most complicated, massive, energy demanding, data volume demanding. It has 2 frequencies, high resolution and very high resolution. Penetrate through the ice and see the subsurface structure. And the ice at Europa is pretty clean ice, so it's pretty much transparent to radar. You'll see a lot. And including on the left here is a picture from Antarctica, again, of some of the subsurface structure they can see in Antarctica through the ice. It may not see the ice-ocean interface because as you get close to the ocean, the solid ice gets warmer and that attenuates the radar signal.
How deep can you go with that?
So that depends on how thick the ice. It can't penetrate water at all. So the upper limit is the thickness of the ice shell, and probably near the base of the ice shell, where the ice gets warm, it gets attenuated as well. But most of the ice shell.
You say if it's goes like 100 kilometers or something, then it's ice. You can see that.
Most estimates say 10 to 50 kilometers. There.
Okay,
so yeah, it should be able to get that deep, especially in the high frequency. The very high frequency sees a shallower depth, but at higher spatial resolution. And many of the questions we have about how double ridges form, how chaos forms, and so forth, we need to know what's happening underneath the surface. So this is the experiment that should tell us that. Here's a comparison of the remote sensing field of view. The radar at 60 degrees should be a circle instead of a square, but then the wide-angle camera has a 48-degree field of view. That's the green box. Then the other instruments are shown with smaller boxes there. Interestingly, although the narrow-angle camera is much higher resolution at 100 kilometers, it's 1 meter per pixel. The UVS, the WAC, MISE, and E-THEMIS all have very comparable spatial resolutions, and all are bore-sided, collect data simultaneously. So we'll have these data sets that go all the way from the UV to the thermal IR. Right, so there's a look at the ground tracks of one of the tours we've been working on. This may not be the final tour, but it's a pretty slide. But the idea here is we have about 50 flybys, and can't get global coverage with most of the instruments. We actually do with the NAC, but most of them, they're sampling, and the goal was to divide Europa into quadrants and get a certain amount of sampling in each one of these quadrants. So it's sort of global sampling at least, if not complete global coverage. These color-coded by altitude. The lowest altitude is 25 kilometers. There's quite a few that are 50 kilometers or lower, more that are below 100 kilometers. Only a few that don't get below 100 kilometers. Okay, now the in-situ experiments. One is the Europa Clipper Magnetometer. And this will characterize the magnetic field of the whole environment. Some easy things to do. What it really main purpose is to understand the ocean. Easy things to do are to estimate the ice thickness and the ocean thickness, which is an important unknown. There's also a requirement on this instrument to place a constraint on the salinity of the ocean. How conductive is it? That's a much harder measurement, and that has really driven this experiment to try to achieve that. PIMS is a plasma instrument, Faraday cups, and it studies the environment around Europa, but also the plasma environment has a big effect on the magnetic signature. You need to be able to account for that to properly interpret the magnetometer data for the subsurface of Europa. MASPEX is the mass spectrometer, very high mass resolution to distinguish among organics as well as permitting isotopic analysis. They show mass of various organic compounds or subcompounds there, for example. The challenge with this experiment is outgassing of the spacecraft itself. It's a giant spacecraft, and they use various epoxies and so forth that outgas. There's a surface dust analyzer, SUDA. This is effectively a dust mass spectrometer that, again, can measure isotopes. It depends on the micrometeorite impacts on Europa, which we have good data on from a Galileo dust detector. It didn't measure the composition, but just understanding the statistics of the impacts and the amount of dust particles kicked up. Good idea of what to expect. And this is from the surface, not gases in the atmosphere, so it's a different composition measure.
If you discover a plume, can you use it for that?
Yeah, sure. If there's a plume, both MASPEX and SUDA really hope we'll fly through a plume. If there are plumes, we don't know where they are. Chances of getting lucky with our current tour don't seem good. It's probably going to be an extended mission, though. So targeting a flyby through a known plume would be a high priority for an extended mission. Okay, gravity science. The number one job, the only requirement is to measure the tidal K2. That's the tidal love number. It's the gravitational counterpart of H2, the love number that's just the altitude, how the altitude of Europa varies over time with the tides. And if there's an ocean with a detached ice shell, that K2 should be a very low value, which means that the surface goes up and down by a large value.
And there's a question whether there is any instrument designed to identify presence of minerals. Is it minerals? What kind?
Yeah, so MISE, MISE is the mass spectrometer for surface minerals. See, gravity science will also look for static gravity anomalies that might be related to density differences in the ice shell or in the silicate mantle. They're not going to see a lot. There's not much topography in Europa. It's very smooth at the kilometer scale, so they're not going to see topography variations. That, in a way, simplifies their problem. How do all these how do these all work together? This is a project slide, envisioning Clipper as a giant Swiss Army knife with all these different tools. I prefer this one, and the elephant, and the blind men are all the different instruments. They each sense one particular wavelength or type of measurement. There's actually 10 of them, not 5 of them. If the 10 blind men all talk to each other, they have some hope, I think, of figuring this out. All right, let's talk about the plumes. This was extremely important to getting approval of this mission. The initial observations by HST were reported by Roth et al. In 2012, and they showed coincident Lyman alpha hydrogen emissions and oxygen emissions extending off the estimated limb of Europa. The resolution and signal noise here is all very marginal. Where to place the limb of Europa is uncertain, but it looks like it extends off the limb, and with both hydrogen and oxygen, that suggests it's a water plume. A height of 200 plus or minus 100 kilometers, H2O column density of 10 to the 20th molecules per meter squared, which sounds like a lot, but it's not. They attempted to replicate this and couldn't do it. So that implies episodic behavior. Some people question whether this is really a plume detection or some other phenomenon or noise. There were more observations by Sparks et al. Of HST again, but this time observing Europa in transit across the disk of Jupiter. And they reported on limb features that could be plumes or could be noise. They admitted that could be noise. Different locations than the Roth et al. Detections. And then there's a third suggestion from reanalysis of Galileo magnetometer data that they interpreted as that the Galileo spacecraft, unbeknownst to everybody at the time, flew through a plume. But the existence of plumes is still not conclusive after all this. But we'll go find out.
So 200 kilometers is a pretty high velocity. Would you expect that geologically?
So, no. If you were to take the best analog to first order seems to be is Enceladus. Enceladus has a self-polar plume that extends hundreds of kilometers, but Enceladus is tiny.
There's no gravity.
Yes, it's a factor of 17 smaller g than Europa. So the same energetics transferred from Enceladus to Europa would give you a plume that was maybe 10 or 20 kilometers tall. That's more of what we expect. We also see some surface deposits that could be diffuse deposits from plumes that suggest even smaller plumes than this. So maybe we'll go there looking for giant plumes and discover small plumes instead. But since the HST papers came out, there have been models that do manage to produce big plumes on Europa. You can make big plumes like that on Io, but that's for silicate temperature eruptions. That's a different ballgame. This is not silicate eruptions erupting through 150 kilometers of H2O.
So what is the possible explanation for that?
For what?
I mean, that high speed.
I don't want to try to explain the models without lots of help. I know they exist. So Europa Clipper, every instrument claims that they can detect and or help characterize plume. I won't read through all of this, both directly and indirectly. So we should, if Europa Clipper doesn't find evidence for plumes, they aren't there. Here's another nice diagram for our space science review paper showing environments in Europa's crust where with processes that might generate plumes or cryovolcanic surface features or other current activity. Includes the diurnal stress in the ice shell, diapurism or ductile ice, convection. There could be freezing, lenses of water melt that somehow relate to all the surface features. And that's a little vague on purpose here. What you don't see here is a fracture extending from the ocean all the way through to the surface and a plume coming out. There's lots of diagrams like that. We worked hard to get rid of it because it doesn't work on Europa. It does work on Enceladus. It's about the same 20 kilometer thickness ice shell, same composition, ice to first order, but factor of 17 lower G makes a big difference in how you can keep those fractures open. You can do it on Enceladus, you can't do it on Europa. So if there are plumes, it's probably erupting from ice. Either the ice shell is much thinner than we generally believe somewhere, or there are ice lenses in the ice shell. There are water lenses, brine lenses in the ice shell. Okay, so Europa Clipper, even though the Europa lander mission is not going forward, Europa Clipper is still likely the precursor to any future exploration of Europa landed mission. It's going to rely on Clipper data. So getting reconnaissance data is still a priority for two reasons. One is to find the most scientifically valuable sites, especially locations showing evidence of recent activity. And that's important because the recent activity can be bringing materials from subsurface to the surface that you want to analyze to look for evidence of life. But also, if it's recent, the organic material hasn't been destroyed by the radiation environment. In 50 million years, you break every organic bond in the upper liter or so of the regolith. So it really needs to find a young spot on the surface. Also, we need to know the surface conditions so that it's safe to land. And we know very little about Europa at the meter scale. This is a cartoon showing some of the processes that are about to occur. I'll talk through all of these, but I will point out that Phoenix lander, run by U of A, had difficulties because of not understanding the Mars polar environment. The regolith stuck in they went to stick it in the instrument, it didn't come out of the shovel, it's stuck there. It was stickier than they expected. And we know the Mars environment a lot better than we know Europa's environment. So this was one of the things that hurt the Europa lander concept. The idea for this Europa lander concept was that it would launch before Clipper even got there. So before we had any Clipper data to know Europa better, it would be too late to change the design. I couldn't resist putting Europa Clipper is not a CubeSat. This is a big spacecraft. The lower right there, it is laid out over a basketball court. And upper right, it's the core of the spacecraft without the solar panels with people for scale. So this is a giant spacecraft. And it is solar powered, so you need to be big to give the power needed for all these 10 instruments on Jupiter, where the sunlight is like 1/25 the strength it is on Earth. Here's a diagram showing the placement of all the instruments of the spacecraft. The current status, this is a picture, there's a website where you can watch them work on the spacecraft at JPL in what's called ATLO, Assembly Test Launch Operations. This is a picture from last week. But at this point, all the instruments and all of the subsystems are integrated onto the spacecraft, except for the solar arrays, which also have the reason antenna on them, which will be delivered to the launch site, Florida, and then integrated with the spacecraft. The solar arrays are giant, shipping them all the way to California, installing them, uninstalling them, shipping them to Florida. You save a lot of effort by just shipping them directly to Florida. So at this point, pretty much everything is there. It's a complete spacecraft, but it's a lot of testing to go still. Thermal vacuum system testing, electromagnetic interference testing, and so forth.
Really going to put in third. I thought JPL gave up on testing. They did theoretically now on film.
Oh, no, not at all.
Okay.
They definitely do thermal. That's absolutely essential.
Okay.
Thermal testing.
I apologize. I thought I read they decommissioned their big chambers. Okay.
Better not have.
Okay.
Alfred, are they still going to go on Space Launch System? Because I know
No.
Okay.
I meant to explain that way back when. Yeah. No, eventually it was clear that the Space Launch System would not be available. It kept getting delayed. The few they have are needed for Artemis. If it was on SLS, it would arrive, in half the time. But after waiting 30 years to get a Europa mission, what's another 2.5 years? So the launch date is October of 24. Jupiter orbit insertion is April 2030. That seems pretty close given the long history of Europa anyhow. Here's what the spaghetti looks like from all the tours and the orbits. And this orbital geometry means we always approach from the leading or trailing hemisphere, and the close approach is always in the sub-Jovian or anti-Jovian sides of Europa. So there's two phases. Europa Campaign 1, there's all close flybys on the anti-Jovian side. Campaign 2 is all the sub-Jovian side. And then in between, you have phasing to move the spacecraft around.
Alfred, is the navigation good enough, or do you have to do your own nav, like where Europa is, so you can get that close?
They think the navigation is good. It'll get even better when we're there and tracking it. But there's not a plan to do optical navigation. It's just radio tracking. So, the Europa Clipper team has a one-team philosophy. Won't go through all this, but basically, we're one big happy team. We're not 10 separate science teams. We share everything, all of our data, all of our software. We plan everything together as one team. Not like Cassini, which was very tribalized. This will be an interesting experiment for a mission of this sort. There's also been a great deal of efforts towards equity, diversity, inclusivity, and accessibility on Europa Clipper. And again, I won't read through all of this, but we even have our own sociologist, Janet Bertesi, providing perspectives on how to do things. We hear from her and others in every project science group and so forth. So UA involvement, Europa Clipper, Lynn Carter is a co-I on Reason. On ICE, and have Sarah McKenzie as ICE affiliates. We have one former faculty member, Jonathan Levine, is on the mission. This is considerably less UA involvement than past large missions to the outer solar system, Voyager, Galileo, and Cassini. But we have 11 UA alumni who are working on Clipper. We're having a big impact indirectly via our graduate students. And there will be participating scientists added around the time of Jupiter orbit insertion. So don't lose hope if you want to work on the mission. Now, I'll take any questions.
You have to end with that.
So,
Sarah.
directly related. The first question online is, for those of us who feel the origin of life question is by far the most important, is there a reason why Europa has taken precedence over Enceladus where we know there are plumes?
Yeah. So officially, we're not searching for life in Europa Clipper. It's studying the habitability. A life search mission would come later, such as Europa Lander, which isn't proved yet. And Europa Lander was in contention in the latest decadal survey. And that decadal survey panel did indeed choose Enceladus over Europa. So Enceladus would be the first place where explicitly searching for life is the goal. That said, there's always hope that with isotope ratios and so forth, you can make the case that there's life in Europa because of life has certain patterns of isotopes and so forth. It would be controversial, but there is some hope being held out for discovering evidence for life in Europa, but explicitly that's not the goal. It is Europa that's been chosen as the first target because we know there are plumes. It's very likely to come from the ocean. You can also land on Enceladus and last for months, not die from the radiation environment so quickly so you have more time to do your work. Ed?
Yeah. So there's a Jupiter orbiter as well. Are there any science resources being set aside for Jupiter observations?
Yeah. Right now, the directive from NASA headquarters is just Europa.
Okay.
Don't pay no attention to that. That psychedelic thing we're orbiting, just ignore that. That's going to change after launch. But for now, we're not. It makes sense to not let other science drive the design and development of the instruments and spacecraft because it drives up cost. But once you've launched, it's too late.
Right.
And then they relax, and I'm sure there'll be some Jupiter system science. And JUICE is there, but there are capabilities on your Clipper has that JUICE doesn't have. So, and having two spacecraft in the system with different vantage points and so forth is quite valuable for such a complex system. So I certainly hope we get some Jupiter system science back, especially IO.
Okay, from you, yeah.
Yeah,
Another photo online, yeah.
I'm really intrigued by the radar observations. I'd like to ask a little bit more of that. You get some global reconnaissance, which allows you to get where the lay of the land, or is it just, a handful of slices that you'll do with this? And presumably you'd like to really search it out for all sorts of stuff.
Yeah, so the radar just sees below its ground track went below about 1,000 kilometers for the ice penetration. Maybe they'll do better than that at higher altitudes. So they're sensitive out to a cone of about 60 degrees, which is to some degree a problem because then surface returns can be confused with subsurface returns, clutter, by mapping the topography, you can sort that out. But no, they're not going to get global reconnaissance at all. But there are large scale features like chaos terrains in Europa. They're going to be well sampled and so forth. Learn a lot from it, but it's not global reconnaissance. Yeah.
Okay, I think Raja, you have a question, right? Would you like to ask in person? He was asking about MISE capability and especially related to how much, plume deposits on surface and as well as the subsurface. How can you?
Yeah. So MISE only detects the surface, but we believe that some of the materials on Europa's surface came from the subsurface.
Right.
Particularly the dark reddish materials are closely associated with things like the chaos terrain and certain lineaments and certain smooth areas like flows. There's a variety of things that might suggest endogenic processing, bringing material up on the subsurface. It does have a different color and it's richer in non-ice components, salts. And so the idea is that infer something about the subsurface composition at least.
Any other question? Any other question from online audience? Bob? Last call? Oh, there's, okay, thank you. Anybody else? Okay, thanks, Alfred.
Yeah.